Hello, my people. I hope we're doing well. A request was made to me about a little bit more guidance on how the last three quizzes were graded. And so I'm going to make these videos, hopefully lead you through, because these, especially quizzes 4 and 5, are extremely important as we move on into Trig. This analytic Trig stuff, the changing of the form of trigonometric expressions, is going to be crucial. Okay, and some of y'all kind of struggle with this. Some of y'all struggled, unfortunately, just with following instructions. Now, on this one, the instructions are very clear. Let me go ahead and zoom in a little bit more. Use the given values to evaluate all 6 trigonometric functions. You must use trigonometric IDs to evaluate. And then I even emphasized it further, parenthetically, no credit will be given if I don't see trigonometric identities used. Show your work, okay? And some of y'all drew me a triangle anyway. Now, I not only did examples of this in class, I did multiple examples of this on the videos, and therefore, those of you who didn't seem to grasp what I was asking, it makes me wonder whether you guys really watch the videos that I create. Like, I can see how many times the video is viewed, and I know that there were 15 of you over the summer. So when a video gets 3 watches, that communicates something to me. Okay, guys? If you're not understanding, and yet you have not availed yourself of all of the resources, then please do go back and do that, okay? This stuff is incredibly important. We're not going to slow down this year, and that's another reason why I want to go ahead and do these videos for you. So let's go ahead and get started. Now, sine x is equal to -3/5. Now, sine is negative in the 3rd and 4th quadrant. But this right here, the only reason that is given is to specify whether it's the 3rd or the 4th quadrant. Now, tangent is positive, where sine and cosine have the same sign, S-I-G-N, like where they're both positive or where they're both negative. Now, sine and cosine are both positive in the 1st quadrant. Sine and cosine are both negative in the 3rd quadrant. So if this one basically is quadrant 1 or quadrant 3, and this one is quadrant 3 or quadrant 4, then of course where they agree is quadrant 3. And that's going to help me when I start having to take the square root and stuff like that. That's going to help me specify whether I have the positive or the negative. Now, that means that sine and cosine are both negative, and so are their reciprocals, and tangent and cotangent are both going to be positive. All right, let's go ahead and start off. I need to find something else besides sine, and so I'm going to use sine squared x plus cosine squared x is equal to 1. Show me the identity, and then plug it in. That's 3/5 squared, and let's go ahead and plus cosine squared x is equal to 1. So cosine squared x is equal to 1 minus 9 over 25. Well, 1 is 25 over 25, so 25 25ths minus 9 25ths is going to be 16 25ths, and therefore cosine x is 4/5 plus or minus. But we've already said that x, the angle that we're dealing with, is in the 3rd quadrant, so cosine, of course, is negative. Now that I have both sine and cosine, I can use the quotient identity for tangent. Tangent is sine over cosine, which in this case is -3/5, over -4/5, which gives me 3/4. Okay, and then of course cotangent x is equal to 1 over tangent x, which is 1 over 3/4, which is 4/3. Now, secant x is 1 over cosine x, and of course cosine x is negative 4/5, so I get negative 5/4. Cosecant x is 1 over sine x, and that is 1 over negative 3/5 or negative 5/3. Notice that I now have the other 5 trigonometric values, and I got all of them by first explicitly stating the trigonometric ID and then using it. Okay, trig ID number 1 to get cosine, trig ID number 2 to get tangent, trig ID number 3 to get cotangent, trig ID number 4 to get secant, and trig ID number 5 to get cosecant. Okay, and then all I have to do is just fill in this little chart down here. And cosine was negative 4/5, this was negative 5/4, this was 3/4, and this was 4/3, and I'm finished. Now you may have gotten all of these values, but if you didn't get them in the specified way, you didn't get any points, because the whole point was to use the trigonometric IDs numerically, okay? To use them to evaluate and find values. And so I was kind of strict about that, but I did actually tell you twice, you must use trigonometric IDs to evaluate. No credit will be given if I don't see trigonometric values used. I mean, I emphasized it, and I mean, I can appreciate the fact that if you didn't study that part, if you forgot to study that part, you at least made an attempt with the trigonometry that you knew to attempt to give me an answer, and I can appreciate that. But the number of people that sort of let this slip kind of was a little disheartening. Okay, let's go ahead and move on. This one said use trigonometric IDs to simplify the expression. This actually simplifies way down. Okay, now. There are several ways that you can do this. The easiest way probably is the very first thing to do is to turn this denominator by means of the Pythagorean identity into sine squared. Once you do that, this cancels with one of those. And once that happens, there's two ways that you can do this, okay? You can either get a common denominator, and you get 1 plus sine x over sine x minus sine x over sine x, at which point it's 1 plus sine x minus sine x when you push them together, right? These two cancel. You're left with 1 over sine x, which is cosecant x. Or, and this is something that nobody did, and it almost seems like it's a mental block for some of you. The great thing about having a monomial denominator is I can separate the fractions. Now, you've spent so many years pushing those expressions together, but you need to remember that any procedure that you've used for simplification can be used, the logic can be run the other way, okay? So basically, I'm going to take that fraction that has a numerator that is a binomial, and I'm going to separate that fraction. And really, it amounts to doing the same thing as we do over here. It just is 1 over sine x plus 1 minus 1, which of course the plus 1 and the minus 1 cancel, and that makes cosecant x. Now, if you didn't make it all the way, I give you some credit, but that is basically that's basically the end result that I was looking for. Okay, because when you're asked to simplify, it's simplify all the way. It's kind of like when you're asked to factor, right? Implied is factor fully. Don't leave anything that is capable of factorization in its multiplied form, unfactored form. Now it says factor the expression and use fundamental IDs to simplify. Okay, let's go ahead. Now, anytime you see something that is 4 terms, it ought to be screaming at you grouping. Now, there's nothing common to the first 2 terms, so basically your GCF for the first 2 terms is just 1. Your GCF for the second 2 terms, however, is sine squared. And remember that once you get here, I think sometimes what we fail to appreciate when we get to this stage is this is basically a 2-term expression. Because while that 4 minus sine x is wrapped up inside the parentheses, its binomial nature doesn't matter, right? And so we have 2 terms right here, and of course the common factor to those 2 terms that you're going to pull out is that. And actually, you don't wind up needing the fundamental IDs, you wind up only needing the factorization, and therefore that is its simplest form. Now, let's get on to the next one. Now, the next one was basically combining the fractions rather than separating the fractions as the example before. And the only way to really do this is to multiply each one by the other denominator over itself. Now, the great part about that is the fact that that other denominator over itself also happens to be the conjugate. And when we multiply by the conjugate of the denominator, we wind up getting the difference of 2 squares, which in this case winds up being also a Pythagorean. Now, we don't really even need to worry about the denominator right now, although we can, okay? What we really need to worry about is the fact that remember, this numerator is functional parentheses, okay? And there's a way to think about that. And the reason why, but we fail to appreciate that on occasion. So let me, if we did it instead of this fraction bar, if we actually turned that into a division symbol, it would be 1 minus sine x divided by 1 minus sine squared x. And then we would need to kind of put like this, minus 1 plus sine x divided by 1 minus sine squared x. And that would be sort of like the elongated non-vertical fraction way of writing it out. And so we can see that what really needs to happen is that negative, when I push these together with that common denominator, that negative needs to be distributed across this binomial. And so you get 1 minus sine x minus 1 minus sine x. And let's go ahead and change the denominator in that same step. You have a positive 1 out in front. You have a negative 1 right here. Boom, boom. And that winds up being, and I saw people actually carelessly multiply those together. They're like terms. They simply combine. So it's negative 2 sine x over cosine squared x. And I'm pretty sure that I actually allowed that as an answer. I simply would have preferred it as negative 2 tangent x secant x. But either one of those got credit. Okie dokie? Now, what we have here in this next one, we are starting with the verification problems. Now, I told you when we started this verification that the great thing about verification problems is that you can do them in more than one way. They're really frustrating part about verification problems is there's no one way to do it. So if you are in love with method, if you're in love with being told exactly how to do something and you need to follow your 1, 2, 3, 4, 5 steps, this was probably a nightmare for you. And that's the difference between thinking mathematically and mere algorithms. But we'll get into more of that as the year progresses. There were several ways to do this one. I'll go ahead. I mean, you either start... Actually, I mean, both of them you start on the right. It's just a matter of, are you going to multiply? And remember, you cannot work across the equal sign, meaning that the principle of what you do to one side you have to do to the other does not come into play here, because this is not an equal sign asking you for what value of alpha is this true. This is saying, is this true for all alpha? And therefore, you have to treat each one of these independently like an expression, okay? So you can't, like, subtract 1 from both sides, okay? Because that would assume the equal sign, which, of course, when you're verifying, the equal sign is the very thing that is in question and looking to be verified, okay? So you can't assume the very thing that you're trying to prove, if that makes sense. Now, there's two ways to go about this. One, I can go ahead and change sine squared alpha into 1 minus cosine squared, and from there factor it and cancel. Or, a little bit more difficult, but if you saw it this way, that's fine. You can multiply this thing by the conjugate of the denominator over itself. Let's go ahead and do it that way first, okay? So we have sine squared alpha over 1 minus cosine alpha, 1 plus cosine alpha, 1 plus cosine alpha. And the whole purpose of doing this is to get to a denominator that is 1 minus cosine squared alpha. Because the moment that you have 1 minus cosine squared alpha, you know that changes by Pythagorean into sine squared alpha. Well, if that's the case, then you didn't need to, basically it was unnecessary to introduce yet another factor into the numerator and denominator. A little bit easier, you could have just gone ahead and changed that numerator into 1 minus cosine squared alpha, and then factored it by the difference of two squares. Boom, boom, and you get 1 plus cosine alpha is equal to, of course, 1 plus cosine alpha, and that verifies, okay? Now, let's go ahead and let's go ahead and move on to the next problem. Now, number 6 and number 7 both had multiple ways to do it, and I'm gonna wind up doing them both ways for you simply because I want you to see both ways. But let's go ahead and look at number 6. Now, number 6 is another one of those problems where you need to, remember the whole mantra, stop, think, then do, okay? Now, the numerator is tangent squared minus secant squared. Now, that is not a recognizable Pythagorean identity, but secant squared minus tangent squared is. And so if secant squared minus tangent squared is 1, then tangent squared minus secant squared is simply -1. You could change the numerator into -1 using a Pythagorean and then just set off to the races. The problem is that actually isn't helpful, or it isn't as helpful. Instead, what you want to do is, let's go ahead and factor the denominator first. It's a binomial, but we notice that both of them have a secant x and a tangent x. That means that what's left here in the first term is tangent, and what's left here in the second term is secant. Then if I factor that numerator as the difference of two squares, boom, boom, all of a sudden I have a difference over a monomial. And if I have a difference over a monomial, I can separate the fractions and simplify. And so what I get here is I get tangent x over secant x tangent x, secant x over secant x tangent x. In the first one, the tangents cancel. In the second one, the secants cancel. 1 over secant is, of course, cosine. 1 over tangent is, of course, cotangent. And oh my gosh, will you look at that. Now, I'm going to show you the other way to do it, and it is ugly and torturous and a whole lot more steps. But let's do it anyway because, you know, fun with math. Alrighty, we have tangent squared x minus secant squared x, all of that over secant x tangent squared x plus secant squared x tangent x, and we want to verify that that is cosine x minus cotangent x. Now we're going to go ahead and do that Pythagorean substitution that we talked about when we first looked at the problem. So that numerator by Pythagorean becomes a -1 because it's basically secant squared. Remember, if secant squared x minus tangent squared x is 1, then if you flip the difference, you simply negativize it, right? And so what we get here is and we're going to go ahead and factor that denominator the same way we did last time. Now, once you get here, you kind of go, well, I've simplified the numerator a whole lot, but I don't seem to have made much headway in terms of the denominator. So, you know, if you're thinking about your strategy sheet, you go, well, if all else fails, turn everything into sine and cosine. Now, the reason that this is helpful is that when you reveal a complex fraction, or the implied complex fraction, that is going to indicate for you what you're going to need to do in order to resolve the problem, okay? And basically you have a problem here in this big denominator. Actually, you have the same problem 3 times, divided by cosine, divided by cosine, and divided by cosine. So in order to undo that, let's go ahead and multiply both the numerator and the denominator by cosine cubed. Yeah, like I said, ugly, okay? I'm trying to encourage you to do it the other way. Now, when you multiply cosine cubed by this denominator, the cosine cubed, the whole point is for it to basically cancel out these 3 denominators. And so what you're left with is 1 times sine x times sine x plus 1. Now, cosine cubed x, and here's the thing, this is another one of those times where I notice that y'all have a problem doing this. If you are given something like, cosine squared x times cosine x, I have zero doubt that you can go, okay, yeah, well, that's just cosine cubed x. And we run it this direction so long that you fail to recognize that pulling it apart, unsimplifying it, is just as legitimate. It's just as true, okay? So what we're going to do here is we're going to do exactly that. And so we're going to pull out a cosine x, and what we have after that is cosine squared. Well, cosine squared is 1 minus sine squared. But negative cosine squared is just the difference flipped, okay? So basically this right here is negative cosine squared. And of course, at this point, you should recognize what you're going to be doing. You're going to be factoring this right here. So you're going to have cosine x, sine x minus 1, sine x plus 1, all of that over sine x, and then sine x plus 1. Boom, boom, those factors cancel out. And what you then get is you need to, unfortunately, you're going to have to distribute. And you're going to get sine x cosine x minus cosine x all over sine x. And again, just like in previous problems, you're going to separate the fractions. And in separating the fractions, minus cosine x over sine x, these signs cancel out, and I'm going to get cosine x minus cotangent x. Oh my gosh! And that was torturous and unnecessarily long, but in the end doable. Okay? All right. Whew. Let's go ahead and get back to number 7. Number 7 also had multiple ways of doing it. Okay? Let's go ahead and let's do it the easy way. What do you say? I felt so bad. So some of y'all were like slaving over this. But the moment that you recognize the fact that sine alpha plus sine beta and cosecant alpha plus cosecant beta, what they have in common is sine. So even if you have to actually write it out this way, that's fine. But hopefully we're going to get to the point where anytime you see cosecant, you automatically think in your head 1 over sine. Now that you've revealed the complex fraction, you have 2 problems, right? The first problem is divided by sine alpha. Well, how do you undo divided by sine alpha? Well, you multiply by sine alpha. The second problem is divided by sine beta. Well, how do you undo divided by sine beta? Well, you multiply by sine beta. So if you multiply both the numerator and the denominator, okay, by sine alpha and sine beta, what happens is, and when we do it in the numerator, we're not going to distribute. We're going to keep it in factored form, and you'll see why here in just a second. Remember, just because you can, now I know the Algebra 1 brain inside of you is going, I must distribute. Fight the urge, okay? Remember that math is not, when you see this, do that. Math is the accumulation of tools that we then learn later to pick up and use strategically. Here, we do not need to distribute. That is not a strategic move. Because now when we distribute this across the denominator, when we multiply it by the first term, the sine alpha cancels, and I'm left with sine beta. When we multiply it by the second term, the sine betas cancel, and I'm left with sine alpha. Oh my gosh, will you look at that? Because addition is commutative, those are common factors, and therefore they cancel, and I have verified. Yay! Now, what we're going to do now is, that was actually the long way. I actually did it first just by not revealing the complex fraction. So basically the shorter way to do this is to skip the turning it into the complex fraction that it implies. And so we can kind of skip that. And let's move on to the next one. Now the next one looks really hairy, but in the end actually winds up being not that bad at all. And the reason is that we can we can use our Pythagoreans to change the form of the numerator. Because remember, sine and cosine related by Pythagorean, okay? Secant and tangent related by Pythagorean. Cotangent and cosecant related by Pythagorean. And the way that they're related is cotangent is equal to cosecant squared minus 1. And so we're going to change both of those numerators into that. Now, there's two ways that you can actually, well, let's just keep going. This winds up being 1 plus cosecant. Okay, we'll just sort of continue that. Now, because the Pythagoreans have 3 forms, and we get the second and the third form by simple subtraction, what we then have, of course, is the difference of 2 squares, and therefore these factor. This becomes cosecant theta plus 1, cosecant theta minus 1, all of that over cosecant theta plus 1, and this becomes cosecant theta plus 1 and cosecant theta minus 1. And I'm going to change the form of this denominator just by factoring out a negative 1 so that it mimics that factor in the numerator exactly. Boom, 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 boom. And what I get here is I get cosecant theta minus 1. And of course, this negative 1 gets applied to both of these terms, minus cosecant theta minus 1. This is a positive cosecant theta right there. Those two cancel, and I'm just left with negative 2. Yay! Now, it says, based on our discussion in class and what I said in the videos, answer the following. I may not work across the equal sign when I am verifying. Okay, verifying IDs. But I may work across the equal sign when I'm doing what I've always done when I worked across the equal sign, which is solving equations. And that, ladies and gentlemen, is the quiz number 4. That's the solution to all the problems in quiz number 4. Now, there may be slight variations on different ways that you actually can do some of these other problems in here. And if you have any questions on that, please do contact me. But I will post not only this document right here along with this video, but I will post the key. I will scan and post the key as well so that you can take a look at that. Be on the lookout for quiz number 5 as well. Like always, just shoot me an email if you have any questions. Bye.